Hello and welcome back to my messy basement for the last time this term. It is the end of week 6. We are finished the course. I'm gonna try and record 2 videos today. One is going to be just what we were doing this week, and then I'm going to record another video that's going to go through that learning outcomes document that I posted to the course webpage under yesterday's lecture section. So let's get straight to it. Here is the set of learning outcomes for week 6, but we're kind of finishing week 5 at the beginning of this week, so let's scroll up a little bit to week 5. So what we've got in week 5, part 2 and part 1. Part 1 is just an introduction to virtual memory, and we kind of started to talk a little bit about things like base and bounds and segmentation when we were looking at this. So explain how a process's entire address space can be provided or supported via the concept of virtual memory. The idea here is that we've got an address space that is either smaller than physical memory or much larger than physical memory, and we are able to support that in either way using these different approaches of virtual memory. Translate virtual addresses into physical addresses. You should now be able to do this for 3 different approaches to virtual memory: base and bounds, segmentation, and paging, linear page tables paging. Describe how an operating system works with the underlying hardware to manage paging in virtual memory. The idea here is the operating system has to do things like set a fault handler. So when someone or a process tries to access memory outside of its allocated range, the operating system needs to tell the hardware, this is how you should tell me about that. This is the code that you should start running. But it also has the responsibility of managing the details of what segments have been allocated or what portions of physical memory have been allocated for a process. And so it has to do things like set registers on the hardware, on the memory management unit or the CPU, like the base and bounds registers or the segment registers or the page table base register. It also has to keep track of making sure that the page table entries, for example, in paging are sane and meet the requirements of the hardware's design. So the hardware tells the operating system, or the hardware manual tells the operating system designer, the person writing the operating system, this is what a page table entry looks like. You have to format it this way. The operating system has to set up the page table that way, and then tell the hardware where to find it. Compare and contrast methods for address translation. So this is kind of like going through the process of looking at base and bounds. Why did we leave base and bounds and move to segmentation? Why did we leave segmentation and move to paging? And why do we use paging now as opposed to segmentation? So thinking about what the differences are between those things, how they're similar to each other, because they are kind of similar to each other in some ways. This was something that we did in class this week. We did an exercise where we were taking a look at comparing paging and segmentation. And then these other 2 learning outcomes, in addition to being in chapters 13, 15, 16, 17, and 20, and 18, we were talking about this in class in a couple of different ways, just in terms of like, well, this is what segmentation is, this is what base and bounds are, these are how the operating system abstractly and conceptually works with hardware to be able to handle those things. These learning outcomes are eligible to be assessed on the final exam, and take a look at that learning outcomes document. But again, I'll go through that learning outcomes document in a separate video. So after we talked about virtual memory, then we talked about segmentation. And with segmentation, one of the first things that we've got here for a learning outcome is discuss the benefits of partitioning memory and address spaces. So partitioning is a keyword that I didn't really use in class. I was using the significantly less formal terminology of break memory into fixed size chunks, but that's what partitioning means. So the idea of partitioning memory is just taking physical memory and breaking it into fixed size chunks, partitioning it into fixed size chunks. Partitioning address spaces is the same idea. So segmentation, we've got 2 or 4 segments. Those are different ways that we can partition virtual address spaces. So discuss the benefits of partitioning memory and address spaces is pretty related to explain how a process's entire address space can be provided or supported via the concept of virtual memory. Explain how, again, so explain how a process's entire address space. This is continuing in this part of week 5 because we're moving from base and bounds into segmentation. Similar to explain how, describe how the operating system works with underlying hardware. This is continuing because we're moving from base and bounds to segmentation. Describe what happens in various parts of the system when a segmentation fault happens. This is in chapter 16, but this is also something we went over pretty extensively in class. I started with a small program that causes a segmentation fault to happen, and then we went through the entire stack. So like, what is that program doing? What instruction is it trying to run that's causing the segmentation fault? What's it actually trying to do there? What is the operating system doing? It's not printing the word segmentation fault, but it's still responsible for doing something. What's the hardware doing? And this is kind of related to describe how the operating system works with the underlying hardware. What's the hardware doing? What's the operating system doing again? What is our process doing after it's tried to do that memory access? And then what's the shell doing? So the shell is part of this whole what happens when a segmentation fault happens, and it's what prints out the word segmentation fault because it's waiting around on the user process and trying to check to see what its return code was. So this was something we did pretty extensively in class. Compare and contrast free space management policies. This was all about taking a look at memory allocation policies. So I used the word memory allocation policies in class, and I tried to make sure that I described them as the same thing, but these are free space management policies. These are like first fit, next fit, best fit, worst fit. This is all in chapter 17. We're talking about free space management policies, and we were talking about it in terms of memory allocators, heap allocators, and we're talking about it in terms of heap allocators even though this is required for segmentation. So this whole idea is required for segmentation because segments are not fixed in size. They're varying in sizes in physical memory. We have to, at the operating system level, keep track of what space is free and not free. So we have to talk about these free space management policies in the context of segmentation, but segmentation isn't actually used by modern operating systems, so it doesn't really fit into an operating system anymore, and it fits more into what heap allocators are doing. Compare and contrast methods for address translations. This is coming from chapters 15 for base and bounds, 16 for segmentation, and we're continuing this because now at this point, you should be able to compare segmentation and base and bounds. So why have we moved from base and bounds to segmentation? What are the limitations of it? How is it similar to segmentation? And then moving on to week 6, discuss the benefits of partitioning memory and address spaces. So this is now chapter 18 is talking about the paging method of partitioning memory and address spaces. We're continuing this because we're building on base and bounds and then segmentation and then paging. The next 2 learning outcomes, very similarly, are we were able to do this with base and bounds. We're able to do this with segmentation. Now we're able to do it with paging. So it's continuing, and we're adding chapters 18 and 20 here. Chapters 18 and 20, in terms of these 2, explain how a process's entire address space can be provided, supported via the concept of virtual memory, and describe how the operating system works with the underlying hardware. Chapter 18 is linear page tables, and chapter 20 is taking the ideas that we kind of got from file systems and applying those to page tables and using indirection and building multi-level page tables. How they work is slightly different, but the concept is fundamentally the same between linear page tables and page directories or multi-level page tables. Explain the operating system data structures and algorithms used to manage partitioning strategies such as paging. So data structures here again are linear page table and page directory or multi-level page table. And compare and contrast methods for address translation. So now this is chapters 15, 16, 18, 20, and continuing. Again, this is continuing because at this point, after talking about paging, you should be able to compare and contrast base and bounds, segmentation, and paging. So how are they similar to each other? How are they different? Why have we moved from one to the next? What are the drawbacks of using one? What are the benefits of using another? All of the methods for virtual memory that we've talked about, segmentation, base and bounds, and paging, they all have drawbacks. They all have benefits that have fixed problems that we've identified with the previous methods for virtual memory and address translation. All right, so like I said, I'm gonna record another video immediately after this one. I just want to make sure that this one is fairly short to describe what we were doing this week. I think that all the learning outcomes that are from this week, maybe with one exception, are going to be on the final exam. But again, take a look at the next video that I post to get a better sense of what's going to be on the final exam. That's it. Hooray, we're finished the course. Good, great, excellent. I hope that you have a great weekend. I will see you on Tuesday. Bye, everybody.